Welcome to the wonderful world of astronomy. As we finish up the unit on the solar system, we're going to take a look at the largest thing, the most dominant thing in the solar system, which is the sun. And this is also going to be a good transition into the next unit when we look at stars. As we study the sun, we're going to learn a lot about stars. The sun is the one star that is close to us that we can study in depth, and it teaches us a lot about stars, and a lot of these lessons we're going to see when we move on to the next unit on stars. So this is part one, a closer look at the sun. Our goals for learning in this video: why does the sun shine, and what is the sun's structure? If you look at these three acrobats all stacked up, I want you to think about each individual acrobat. The one on the top, just as he does every day in life, is just holding up his own weight. But think about the person in the middle. He is holding up his own weight plus the weight of the person above him. So he is under a good amount of pressure from that person above him. But the person on the bottom is holding up a tremendous amount of weight. He's under a lot of pressure. Not only does he have his own weight that he holds up, but the weight of the two people above him. So the deeper down you go in this stack, the more pressure there is. The weight of upper layers in the solar atmosphere compress the lower layers. So with the sun, and this is the same with Earth's atmosphere, and you've seen Jupiter, talking about the deeper you go into Jupiter, the more pressure there is. You think about Earth's atmosphere. Above you is about 60 miles of air. So there is air pressure that you are feeling that comes from holding up the weight of a column of about 60 miles of air. So the way this relates to the sun is that the deeper you go into the sun, the higher pressure there is. With the sun and with all stars, there is a contrast of forces. There is pressure from radiation that is pushing outward, and there's gravity pushing inward. And so the sun has what's called gravitational equilibrium. The energy supplied by nuclear fusion maintains the pressure that balances the inward crush of gravity. Now, if you look over at the picture, the green arrows show gravity crushing in, the red arrows show the pressure from nuclear fusion in the core pushing out. And imagine if the core shut down, if it didn't have nuclear fusion, then it wouldn't be creating that outward pressure, and the sun would just crush inward by gravity. And that happens to a lot of stars when they come to the end of their life. But fortunately, the sun and most stars have this equilibrium, this balance of pressures. As we go into the unit on stars, I want you to keep this in mind, that every star has this balance of pressures, gravity crushing inward, and there's got to be something pushing outward, some pressure pushing outward to maintain that equilibrium. There's an energy balance in the sun. The rate at which energy radiates from the surface of the sun must be the same as the rate at which it is released by fusion in the core. So nuclear fusion is a process that I'll talk about later. It's the process by which the sun produces energy, the light and the heat inside the core, which is represented by this red ball in the center. So it produces so much energy. There's got to be the same amount of energy that escapes from the surface of the sun. If there were not that balance, then there would be a buildup of energy inside the sun. And there couldn't be less energy or more energy escaping than is created inside the core, because that would be creating energy out of nowhere. The sun, when it originally formed, and we talked a little bit about that, the formation of the solar system in chapter 8, and we're really going to get into that in chapter 16 when we look at the birth of stars. But as we think about when the sun first formed, it was a protostar, or we can also call it the protosun. And as it was forming from a large cloud, we talked about that in chapter 8, there was gravitational contraction. It got smaller and smaller as gravity pulled it in. And that provided the energy that heated the core as the sun was forming. It got smaller and hotter until it got hot enough for there to be nuclear fusion in the core. So the contraction stopped when nuclear fusion began, and then it was officially a star. Some facts about the sun. You've seen before that it is the largest by far object in the solar system. It is in diameter 109 times the Earth's diameter. Its mass, it's about 300,000 times the mass of the Earth. Its luminosity, otherwise known as its brightness, is 3.8 times 10 to the 26 watts. Now remember scientific notation, that's a 3, an 8, and then 25 more zeros after that, watts. Which means that every square centimeter of the sun is 6,300 watts. Now you compare that with a light bulb, like a 10-watt light bulb or a 20-watt light bulb. The entire light bulb gives off 20 watts. Every square centimeter of the sun's surface gives off 6,300 watts, and it is so large, it has a lot of square centimeters to it. So that gives it this extremely large luminosity. Here you can see roughly to scale the Earth compared to the sun. And notice these sunspots. We'll talk about these later in this chapter. What exactly are sunspots? Some of them sometimes are larger than Earth. Now, I say sometimes. Sunspots are very temporary. Some of them only last a day or two. The most long-lived ones might last 2 or 3 weeks. So they come and go, but sometimes they can be larger than the sun. Let's take a look now at the sun's structure. There are many parts to the sun. Now, as you look at this picture, it shows these different layers of the sun. And these are not discrete layers, meaning if you think about in a textbook, the bones of the body, you've got your femur and your humerus and all these different bones, and they are these discrete objects. And this picture wrongly implies, perhaps, that there are these discrete areas. There's the core, and then that suddenly stops and it leads you to the radiation zone, which suddenly stops in the convection zone. The reality is the sun is a big ball of gas, more specifically, a big ball of plasma. There is no discrete, definite ending of the core and beginning of the radiation zone, but rather these zones are what astronomers have designated where different things are happening in the different zones. So it's a continuum as it goes from the inside of the sun, from the center to the outside. And we're going to look at each of these zones of the sun. Let's start at the center of the sun. In the core, it's designated in this picture by a red ball. The core takes up about 1/4 of the radius of the sun. It's where energy is generated by nuclear fusion. So that's where all the sun's energy comes from. In a later video, we will look at nuclear fusion, what exactly that means, but it happens in the core. The core is a temperature of roughly 15 million Kelvin. As we move outward, the next zone is the radiation zone. So we've moved outward to a cooler temperature. On average, the radiation zone is about 8 million Kelvin, and it's too cool in temperature for there to be nuclear fusion. So no energy is created here, but it's where energy is transported outward by photons that were created inside the core. Next, as we move outward, is the convection zone. This is where energy is transported upward, or we could say outward, by rising hot gas. You see it's represented in this picture by these circles with arrows. The idea here is that gases are rising towards the surface, they cool off, and then they fall back down. So they're convecting up and down. Next, we get to the photosphere. Sometimes astronomers refer to the surface of the sun or the surface of any star, and that's the photosphere. Now keep in mind it's not a solid surface, but if you think about a picture of the sun, the yellow ball that you see, that is the photosphere, the surface of the sun. So it's the visible surface of the sun. It's a temperature of about 5,800 Kelvin, and that's the temperature that gives the sun its yellowish white color. The photosphere is less dense than Earth's atmosphere. So when we started in the core, it was very, very dense, much denser than lead even. But as we move out, there's less and less pressure, and now we get to the photosphere, less dense than Earth's atmosphere. Visually, as we're moving out of the sun, we've left the surface of the sun. But I want you to understand there's still more of the sun to go, just its parts that you don't see with your eyes. The next layer is the chromosphere. It is a temperature of about 10,000 Kelvin. The high temperature means it emits ultraviolet radiation. So let's think about this. As we've moved out from the core, which was at 15 million Kelvin, and we've moved out, I said the radiation zone is about, on average, 8 million Kelvin. We moved to cooler temperatures in the convection zone. Photosphere was 5,800 Kelvin. So as we're moving out, we're going to lower pressure and lower temperature. Now, as we've moved out to the chromosphere, suddenly the temperature increases. And that has to do with magnetic activity on the surface of the sun that accelerates the electrons, it accelerates the charged particles. And remember back to chapter 5 that temperature is really a measure of average kinetic energy of particles. So the particles are accelerated, meaning they're going faster, and so they have more kinetic energy, they have a higher temperature. Something important to keep in mind, don't ever look at the sun, even and especially during a solar eclipse. Now, I say especially during a solar eclipse because during normal daylight conditions, most of us are not prone to wanting to look at the sun. It's just too bright. But an eclipse is deceptive because it's dark outside. If you're ever in the presence of a total solar eclipse, it's dark outside. And the big feature that everyone will be talking about is the sun and how amazing it is. Still, don't look at it. During an eclipse, the moon blocks the photosphere of the sun, but not the chromosphere and the corona. So you can see this picture of a solar eclipse. The moon is in front blocking what we call the bright part of the sun. But there's still the chromosphere and the other layer I haven't described yet, the corona. The chromosphere emits ultraviolet radiation, which can damage your eyes. Aiding the damage is the fact that because it's dark outside, your pupils are opened up to accept as much light as possible. So make sure if you're ever in the presence of a solar eclipse, proper eye protection should be used. The last layer of the sun is the corona as we move outward. And this is where particles, the charged particles of the sun, are moving even faster. So it's actually up to a temperature of about 1,000,000 Kelvin. It's very, very thin, and so there isn't much thermal energy, but the particles are moving very fast, so they have an average, very high average kinetic energy. So it's about 1,000,000 Kelvin, and given that it's that temperature, it emits X-rays. Moving beyond the corona, we have the solar wind, which is not actually part of the sun, but it's the charged particles that have left the sun and are streaming outward through the rest of the solar system. So the solar wind is a flow of charged particles from the surface of the sun. As we think about the electromagnetic spectrum, I want you to remember this. To the left with the high frequency, the short wavelength is gamma, X-ray, ultraviolet, then we have visible light, infrared, microwaves, and radio waves. And here we're at low frequency. The sun gives off many parts of the electromagnetic spectrum. The corona, the outermost layer, at about 1,000,000 Kelvin emits X-rays. The chromosphere at about 10,000 Kelvin emits ultraviolet radiation. And the photosphere at 5,800 Kelvin emits visible light. So what have we learned? Why does the sun shine? The sun shines because gravitational equilibrium keeps its core hot and dense enough to release energy through nuclear fusion. What is the sun's structure? From inside out, the layers are, and I want you to have these memorized, and I want you to know some key features of each of these layers. But we have the core, radiation zone, convection zone, photosphere, chromosphere, and corona. Again, be sure that you can list the 6 layers of the sun in order from the interior outward. So we have the core, radiation zone, convection zone, photosphere, chromosphere, and corona. Make sure you know those. Test yourself. In which region of the sun is energy produced by nuclear fusion? I want you to remember that that's only in the very interior of the sun where energy is produced, and that's in the core. Which region of the sun is thought of as the sun's surface? The photosphere. An easy way to remember that, it comes from the Greek photo, that comes from the Greek word for light, and like a photograph is basically a print of light, a writing with light, and so that's where we get the light of the sun from. That's the light that we see, the photosphere. What is the temperature of the photosphere? Now, 2 of these temperatures I've mentioned in this video. Actually, 3 of them I've mentioned in this video. Answer A, 15 million Kelvin, that's the core of the sun. 1 million Kelvin is actually the outermost layer. That's the corona. 300 Kelvin, by the way, is that's roughly room temperature. That's clearly not the answer. The answer is 5,800 Kelvin. Most of the sun's ultraviolet radiation is emitted from this region, which has a temperature of about 10,000 Kelvin. And I want you to remember that's the region above the photosphere where it starts to get hotter. The chromosphere. That's it for this part 1 video, a closer look at the sun. Have a great day.